Good morning. So we're going to introduce space-time diagrams as a geometric way of interpreting how space and time change relative to different frames of references. So this is nothing new in terms of what we've learned in regard to the algebra. It's just now we're going to take a geometric point of view. You may find this a little bit more straightforward than what we've seen with the algebra, or you might find it confusing, but like with anything, practice will help. So I'm going to give you the basics of what a space-time diagram is, how we can plot certain events, and then maybe start looking at different frames. So that's the goal here, with the practice really filling in all the blanks and showing you how we can use this. So let's just try to use this time to establish the basics, and obviously if you have questions, we can address them. Okay, so first, what makes a space-time diagram a little bit different than a regular plot of position time is that we flip the axes. The going on the x-axis is where you are, x, and it can be positive or negative. And you know, we always, in almost all problems, the event or events in question start at some position 0 at some time 0. It's just a very convenient way of doing it. And we can denote the units in light years, light seconds. Usually in these problems it doesn't matter. It's just some arbitrary distance. And then along the y-axis is time. And it's a little bit odd with time in that it's technically, we often call it CT. And if you think about this, C is the speed of light times time is a distance. So notice those years, or excuse me, the units are the same here. So the idea is if we travel for 1 year in time, we go at the speed of light, we go 1 light year. If we travel 2 years in time, 2 years at the speed of light, then we go 2 light years. So it's just a convenient way of, rather than just leave this as a time, so that we got the same units going forward or horizontally and vertically, we just throw a C in there. It's not a big deal for most of what I've seen. It's just that it's a convenient way of expressing it. Sorry, I'm being not clear on that. Okay, so that's the key thing here. All right, so I've already addressed these 2 points. All right, so now let's just do some sample events. So I've got 4 events listed below, A, B, C, D, and I just want to show you how we would have just highlight some very simple ideas on here before I get to more perhaps interesting situations. Okay, so again, an important thing to understand, it's just always convenient to I guess I should make clear that almost always we start in the rest frame. Our initial axes are in the rest frame where the observer is not moving. And when there's something else moving to it, which we'll get into in a little bit, we want to synchronize at least at time 0 and position 0. That's where our arbitrary starting point is. Okay, so the first event is you observe a beacon that is 2 light years away, a beacon, some light source, but it's not moving relative to Earth. And you want to show what it would look like on what we call the world line. What is it doing in space and time? Okay, well, so 2 light years is over here, and then what's going to happen is this object, since it's not moving relative to the Earth, isn't moving through space, x, but it is moving through time. So its world line would look like this. It is staying at position 2, but it's moving through time indefinitely. Okay, so we just get a vertical world line. And so one thing we can see, vertical world lines are events that are not moving in space relative to the rest frame. Now, I don't have a specific one here, but I'll get to that later. I'll finish that, sorry. Is if it's not moving through time relative to us, well, that doesn't make any sense. Things have to move through time, so I just realized why I didn't say that. Okay, so let me go back. Let's look at another one. So now we have a spacecraft B leaves the Earth at a velocity of half the speed of light and in a positive direction. Okay, so how would we plot that? So if I go to a different color, again, we're going to assume we start here. We don't have to, but we're going to start here at position 0. It's leaving the Earth. Let's say that's our rest frame. And it's moving half the speed of light. Well, we want to indicate the half the speed of light. Well, speed is the distance divided by time, but and usually that's slope on a graph, but since our position's here and time is here, it's going to be the inverse slope. Regardless, since it's a half, it doesn't matter, so we are going to go, I'm sorry, it doesn't matter here. We are going to go over 1 up 2, right? Go over 1 up 2. So if we connect those, all right, there is situation B, okay? So a key idea here is that inverse of the slope of the world line is equal to the velocity of the object relative to the rest frame. Okay, so that's just a little adjustment you might have to make since we're so used to sloping the velocity here. We got to do the inverse slope. All right, next one. Spacecraft heads back to Earth at a velocity of negative, okay, 0.25 c, and it takes 4 light years or 4 years to do so. So where we would start there to fit that all together is we're going to start at time 4. It's going to head back to the Earth, okay, and to go negative 0.25 c, I've got to go over 1 down 4, and you can work out, there's our negative slope, that's our negative velocity. It takes 4 years to do so. So that's what that would look like. So again, we can just show going backwards as well as forward. And then the last one, this is going to be important down the road. Spacecraft D is initially at x equals -3 light years, and it sends a light signal back to Earth. Okay? So we are going to go, so we're going to say it's at time 0, that's where it is. So if I go over to -3, 1, 2, 3, here is where spaceship D is at time 0. It sends a signal back to Earth. Okay, so what do we know about that signal? It's light, so it has to travel at a speed of c. So where do we see the speed of light here? Well, that's where these nice units that we chose here. In other words, if we travel for the light travels for 1 year, it's going to go 1 light year, and then another year, it's going to another light year. In other words, it's going to look like this. Okay, and the important takeaway from this one is that the slope of any light signal, regardless of whether you're moving or not, because we know that the speed of light is the same in all frames of reference, is always plus or minus 45 degrees on the world line. Okay, so that will be important, like I said, down the road. So go back and look at those. There's a lot of little information in there that, we don't have a ton of time to look at right now, but you want to make sure you have. Okay, so let's look at another example. E. So we're looking at 2 events. So 2 light flashes flash simultaneous from point A, right, or event A at x equals 1 light year. So I'm going to go over here, and B equals 3 light years. So I have an A there and a B there. Okay, oh, I'm sorry, I didn't finish it. At time equals 1 year. Okay, so it's some arbitrary time. It occurred at 1 year, so that's 1 year and 1 year. Okay, so the fact they occurred simultaneously means that they're at the same position on the y-axis, and that takes us to another point. Points that lie parallel to the position axis, in other words, parallel to this, it occurs simultaneously. And simultaneity is going to be a big thing when we look at more complex problems down the road. Okay, I think I spelled that right, simultaneously. Okay. So again, we have 2 objects, stars, beacons, whatever, that position 1 light year and 3 light year. At some arbitrary time 1 year, they send out a flash of light. And then we can ask, when is that flash received on Earth? Well, you could do simple kinematics to figure that out, but we want to use the space-time diagram here. So here is our first event, and so light is emanating from it. So how does light behave? Well, it travels at the speed of light. So it goes off in all directions. It would go this way, and it would go this way. And we are interested where it hits the timeline of the Earth. Remember, that's the frame of the Earth. So we can say that if this is flash A, this is event A or a B, that A is going to hit it at 2 years. And then if I go to B, which again, light is, right, then it's going to hit at 4 years. Okay, so it's a convenient way using this space-time diagram to plot out how things are going to behave. We could just as well do this algebraically, but we'll see down the road why this is a nice way of doing it. Okay, so let's continue on. We'll do one more example. I won't get through it all, but we'll pick up on it in class. Okay, so now let's use world lines to visualize events as seen in different frames of reference, S and S prime. Okay, so I have a grid here, and again, that's assumed to be S. That's the rest frame. We've got our labels right there. Light years isn't so much the important thing here. It's just that time is on one axis and X is on the other. Okay, so what's our event? Axel watches B leave a spacecraft that moves at 60% the speed of light, relative to Axel, and heads towards a planet that is 3.6 light years away. Okay, so we could ask how much time passes from Axel's frame. How long does it take B to get to this planet? Well, that's pretty straightforward. Okay, technically it's, since the clock is moving, in other words, it's B's clock that's moving, this is T prime, but we don't need to necessarily know that. We can just say it's simply the distance it travels, 3.6 light years, right, divided by 0.6 c, the speed of light. So 3.6 divided by 0.6 is 4.8, and you can work out the units. That's just going to turn out to be years, okay? So we know it's going to take 4.8 years for B to get there. So now we want to plot the world line for B from Axel's frame. Axel's frame is the rest frame, so this is pretty straightforward. We have two coordinates. We have a position coordinate, 3.6, so 2, 3, 3.4, or excuse me, 3.5, and we found that it took 4.8 years. So I'll go up to 4, 5, so it's going to be right around there. Okay, that's where, wait a second, did I do that right? Sorry, this was not 4.8 years. This was 6 years. Okay, I did my math wrong. So we're going to go up to right around here. And if we connect the two, so here is the world line for B relative to Axel. Okay. Now, what does B see instead? Well, we can do our standard Lorentzian transformations and use a time dilation, which we'll do here. But later on, which I'm not going to have time in this tutorial, we're going to show how this can be done by changing the grid. So we can ask how much time passes from B's frame. Okay, well, it's not going to be the 6 years because she's moving relative to Axel. Axel is in the rest frame. So this is really the proper time, and we know that the proper time is going to be equal to Axel's time divided by the gamma factor. Okay, now I haven't worked out the gamma factor yet, but we know that gamma is going to be equal to 1 over square root of 1 minus v squared over c squared. Plug